Welcome to today's Explainer. Let's get right into it. A major reason modern drug discovery fails actually has nothing to do with the resolution of static protein structures. It's because we often ignore one fundamental truth. Proteins are absolutely not rigid statues. They are dynamic, moving fluids. Today, we're going to break the mold and explore a radical new physical computing paradigm that's set to completely disrupt traditional digital supercomputing. Here's our roadmap for today. We'll start with the dynamic soul of proteins, look at the fragile borders of digital computing, and then dive into analog physics solving with facts. After that, we'll cover its incredible resilience against thermal noise, look at allosteric drug virtual screening, and finally, put out a call for pioneers of physics. All right, let's jump straight into Section 1, the dynamic soul of proteins, moving way beyond static structures. So AI models like AlphaFold are absolutely brilliant at predicting static structures, right? But honestly, this creates a massive cognitive mismatch. In the real world, a crucial allosteric switch, that exact split-second shape a drug needs to bind to, might only exist as a rare conformation on a microsecond scale. Trying to capture this continuous dynamic fluid using discrete digital snapshots, it's literally like trying to understand the entire ocean by looking at a single photograph of a wave. And here's the crazy part. Just to capture one single microsecond of this dynamic movement, traditional digital molecular dynamics requires something like 500 agonizing steps of gradient descent. To even attempt to catch up with this biological timescale, supercomputers have to crunch data 24/7 for weeks, burning through hundreds of kilowatts of power just to simulate what nature does naturally in a fraction of a second. Moving on to Section 2. The fragile borders of digital, and why this binary mismatch is such a severe bottleneck. When you force biological reality into a rigid, clock-synchronized digital architecture, you inherently create systemic fragility. Digital chips demand absolute perfection, but in the real world, which is full of thermal noise, if the timing is off even slightly, the digital system can't just adapt. It crashes, or it completely freezes up. This leads to an almost absurd situation. Under environmental stress, digital supercomputers are forced to sacrifice over 30% of their total bandwidth to passive error correction, or ECC. We are literally wasting massive amounts of power, not to simulate biology, but simply to keep the digital hardware from collapsing under its own strict binary rules. Let's pivot to our third section, analog physics solving using facts, specifically looking at the CSDL version 1.4 framework. The chip doesn't compute the answer. The chip becomes the answer. This quote perfectly captures the core philosophy of facts, the fully analog computing system. We aren't executing code here. There's no clock frequency. We just load the voltage vectors and let the physical hardware naturally relax into a stable state. The physics of the circuit literally becomes the mathematical solution to the protein's energy landscape. This is where the CSDO framework's mapping is just so elegant. We take the 20 amino acid residues and map them directly to N-node voltages, or V-node, in an OTC array. Then, potential energy functions, like Lennard-Jones and Coulomb forces, are mapped directly to hardware consistency constraints, meaning the absolute difference between xi and xj is less than or equal to epsilon ij. Finally, the hydrophobic effect is mapped to magic sum hypercube constraints, ensuring the sum of all xk equals m. It is a pure one-to-one physical mirror of biomechanics. And the results of this physical mapping? Absolutely mind-blowing. Unlike AI models that require millions of multiple sequence alignments for training data, FACS requires 0 training data. A single conformational relaxation takes just 1 microsecond and uses a tiny 50 milliwatts of power. To put that in perspective, that's the equivalent of achieving 33.3 megaflops of iterative solving in just 1 single microsecond, a feat that takes this 500 steps of gradient descent in the digital world. Let's hit Section 4, resilience against thermal noise, and how we actually put biological stress mechanisms into hardware. Based on the validated virtual fab data, we introduced external thermal noise to simulate physiological temperature fluctuations, a sigma of 0.03. And get this, even in an environment equivalent to deep space radiation, the system still maintains 99.9% of its effective computing power, scaling well into the teraflops range. But what makes this truly revolutionary is the biological stress mechanism introduced in CSDL version 1.3. When external thermal noise spikes, FACS doesn't crash, instead completely mimicking the conformational plasticity of real proteins adapting to heat. The system automatically increases its local time constant, tau, from 16 picoseconds to 41.5 picoseconds. It gracefully slows down its relaxation time to guarantee a zero-error output. That's the brilliance of analog circuits natively filtering noise. All right, Section 5, allosteric drug virtual screening. This is real-time physical problem solving in action. Imagine targeting notoriously difficult proteins like KRAS mutations. Researchers can encode the known dihedral constraints of the target protein right into analog memory. Then, using hardware potentiometers, you literally inject the candidate drug disturbances in real time. You can watch the relaxation paths directly on an oscilloscope to instantly verify if it settles into a new low-energy stable state. We're no longer relying on statistical inference. We are physically feeling the binding affinity in the hardware itself. Finally, Section 6, Seeking Pioneers of Physics. This is our call to action. We want to be completely transparent here. We don't have a physical test chip in our hands just yet. However, the heavy lifting is done. The variational principles and global Lyapunov stability are mathematically proven. We have the complete physical memory mapping and virtual fab data ready for standard 40-nanometer libraries. Right now, we are actively seeking partners in computational biology and pharmacokinetics to take this hardware-agnostic physical paradigm into real wet lab validation using FPGA or OTAC test chips. As the saying goes, Einstein didn't have a particle accelerator when he published the theory of relativity. Groundbreaking physics and paradigm-shifting frameworks always precede the final hardware fabrication. We aren't promising a magic off-the-shelf chip today. We are offering a mathematically proven, physically accurate mapping. So I'll leave you with this final thought to challenge all you visionaries in biology and drug discovery. Are you going to keep waiting weeks for static approximations from digital supercomputers? Or are you ready to join the analog revolution and finally uncover the true dynamic soul of proteins? The math is proven, the mapping is ready. Thank you so much for joining me in this explainer, and we'll catch you next time.